Hello everybody, and welcome for the fourth lecture on causality, and here today we will look a little bit in a practical manner and in a less, let's say, formula-driven or mathematically driven way to causality. And the reason for why is that I'm perfectly aware that when facing a new method, one needs time to make things settle down, and then one needs often to come back to the new concepts and trying to interiorize them, try to make the dust settle and let the vision be clear. So we will face a practical problem that we speak about last time, about football, association football, or soccer if you are from the United States. But if you are from the United States, you don't know what soccer is unless you are a woman. And we will see some basic concepts of graphs, and we will see the meaning, the actual meaning of a direct acyclic graph in sort of a methodological and philosophical manner, and then we will go further beyond, and let's see what we can do and what we can do not with graphs. And of course, if you have some question, if you want to intervene in this lecture, I plan full of space for direct intervention. So when you want to say something, when you want to agree or disagree with what I'm saying, please raise your hand and make me know. And if you remember, the question I was starting from the last time was a very personal question that concerns to me, actually, as being a supporter of Torino Football Club, and is asking me how would Andrea Belotti play with Milan. Andrea Belotti is a striker, the striker of my favorite team, Torino FC, and I'm actually quite a little bit concerned and scared for the fact that you could choose not to refresh his engagement again with Torino and start playing with Milan, that is managed by Stefano Pioli. I would have liked to insert a photo of Andrea Belotti with Milan jersey here, but I wasn't able to do it. But the question is, how can I estimate the performance of a single player in a situation in a new society, given the things that I know? If you consider it a little bit, if you try to think a little bit about it, we've been speaking up to now of distributions. We were thinking about men and women and treatment, yes or no, and on recovery, yes or no, on populations. And we faced distribution of these outcomes and of these treatments on populations. But here I'm speaking about a single person, a single player, and a single coach. How can I speak about this in causality, in a causality way? Well, the answer is that I have to go to distribution again. I have to go I have to go in a situation where I can speak about distribution of events. I can speak about probabilities. I can speak about every single thing that can happen and estimate a probability of it. And then I can bind them to the single player, to the single actor. Because of course I'm speaking here of football, but I could speak about a new worker that can be or cannot be hired by a new company, and I want to estimate his performance in this new company, in this new firm, in this new working environment. But unfortunately, I cannot experiment it. I have to estimate it from data. So why? And this is a little bit an introduction about this. Why speaking about football, and why you will often hear me speaking about football, about association football. There are two main reasons for doing that. And one of the main reasons is, of course, that we've got plenty of data. If you, when you watch a football match, you see that players are wearing this GPS, this sort of a space tracker that makes me know second by second or split second by split second where they are, at which speed they are going, in which direction they are going. I can reconstruct all the football match, and I can assign probabilities to events, to chain of events, to geometries, to patterns, to actions, and then I've got a lot of data. And as a data scientist, I am quite happy about it. But there is another reason why I speak so often about football. And I would like you to think a little bit about it. So I'm here posing for the first time, and I will ask you why, in your opinion, I am so often speaking about football. So if you have your hypothesis, whichever hypothesis it is, please raise your hand and let me know what is your opinion about it. Of course, I have my opinion, but I would like you to try to activate and try to give me your answer. So I know for sure that some of you is thinking. Unfortunately, we have got Luca here that will for sure give his opinion. If no opinion is given me in 10 seconds, I will ask a volunteer to answer me. Of course, like in the army. Of course, Leonardo would be the chosen one, since his name is the same name of my son. So I have got a predilection for people named Leonardo. Leonardo, can I ask you for your opinion? I'm allowed to ask for your opinion.
Hi, can you hear me?
Hi.
So the exact question was, why do you choose football as an example, right?
Exactly. And the same, I told that one reason is that there are lots of data. And so we have many data. But there is another reason, and I would like you or others to infer the possible reason.
Is it a good reason, or could it also be just the fact that a lot of people have opinion about football and not often they have good data to support those opinions?
This is a very good answer. So we have plenty of opinions. So we have a possibility from experimental point of view to let's say compare the average opinion, the opinion of the expert, the opinion of the layman, and let's try to see where they merge, because sometimes there is a very interesting book by Gerd Gigerenzer, a scientist, German scientist, about the wisdom of the crowd, that often in popular sports, the wisdom of the crowd is superior to the wisdom of the expert. So this is a good point, but there is another reason, and of course this is a very valid reason. Do not think that I'm saying that mine is the better, but I've got something else in mind, and I would like you to try to give me your opinion, because probably you've got some idea that could be better than mine. And I would like to hear from you. So thanks, Leonardo. If there's anyone else, no. If there's not anyone else, I will give you my opinion, and my opinion is that football is very similar to life in one aspect. The most important event in football is the one that happens the most seldom, the one that happens less, the goal, scoring a goal. If you look at basketball match end up with a 90 to 80, 100 to 90, 110 to 105. Lots of points are scored. If you look at a tennis match, lots of points are scored. If you look at a volleyball match, lots of points are scored. If you look at a football match, and if you look at the distribution of goals scoring during a match, they peak at 3. 3 is the most probable number of goals that are scored during a match. The most important event, goal, is the one that happens less. So we have a problem, and we have face it with reality too, because probably try to think about the most important thing in your life. When you know a person to which you could engage, when you decide at where university to study, or which place to go work, you want to go working, or in which city you want to live, or if you have to buy this house or that house, or which treatment you should undergo after having been diagnosed with cancer, or with that, or with other diseases. These are things that happen seldom. Important things in life happen seldom, but we have to decide about them. So football is a wonderful social lab for many reasons, and for me, as a data scientist, the most important, the most interesting reason is that the most important thing is the one that happens more seldom. So I can't count goals to say which team is the stronger. I would never get anywhere. I have to find another way. So let's try to find this other way, and let's try to find where this is connected to causality. Let's try to infer this causal scheme. This is my causal scheme. Is causal scheme that I imagined to to judge the situation, the ability of a player in a team. And I draw this causal diagram. The coach, the manager, in English terms, in this case, let's call him Stefano Pioli, the coach of Milan AC, decides which player play. So he decides the lineup. So it's not the player that decides who is the manager, unless you call yourself Leo Messi, but this happens quite more seldom than the goal. So the coach decides the player, and the coach decides, or better, causes the situation, because a coach has his own tactic style. The coach decides his own tactical styles, and here there is, of course, there is an arrow that is missing. If you imagine, and you saw it in what I've said, I can imagine, of course, that even the player decides about the situation. Of course, the player plays. Marquis de la Palisse would have said this in these perfect terms. The player plays. So here I can have my causal scheme. The coach decides the player and the situation by means of these tactical indications. The player decides the situation because, of course, a player manage the ball and manage the space with the players around him, and so he can influence the situation. Of course, the player decides directly the outcome, because imagine that you have a player in the area, in the large area, the one in which the goalkeeper can take the ball with his hand, and the player is shooting. If that player is Romelu Lukaku or Zlatan Ibrahimovic or Andrea Belotti, well, I can expect for a positive outcome. If this player is Tommaso Rincon from Torino, or if he is Simone Verdi from Torino, or if he is Simone Zaza from Torino, all football players, but not with good feats, let's say, I would expect not a positive outcome. If the player is Marco Malvaldi, for sure this will not be a goal. Or if the player is Darko Panchev, those of you who are old enough to remember this player, this legendary player, able to miss the goal from a average distance of 3 meters, it's very, very difficult to shoot a goal. So the player decides the outcome, but even the situation decides the outcome, because if I shoot 30 meters away from the goal, you have some probability. If I shoot 3 meters away from the goal, is another situation, a more easy one. And if I shoot, given a cross, given a suggestion, let's say a pass from a very good passer, passer, let's say the late Andrea Pirlo or other players, it would be probably an easy ball, and with the right speed, the right velocity, the right position, the right spin, so it will be very easy to put it into the goal. But if the ball is, let's say, not given with sufficient precision, for example, if Simone Verdi of Torino passes it to you, it will be not easy. So situation and player both decide the outcome. I would like from here to estimate the performance of the player, so the probability to have a positive outcome given that that player plays in, given that that player, how could I afford this situation? It is possible, in your opinion, to study this situation? And here again, I ask for your opinion, and I will wait a little bit for you to give me. If nobody does, Leonardo, prepare yourself, because you understood that you are my favorite victim. How can I estimate the effect of Belotti in this kind of situation? Well, here we face a problem. I will give you a hint. In order to evaluate the impact of a player in a situation, and a player of a situation and of a coach on an outcome, you have to calculate the probability. You have to calculate the probability of an outcome given that three situation. But here we have a little problem. Imagine the causal scheme that I showed you before. I can imagine the probability of scoring a goal in a process, in a given process, forcing Belotti to be on field and Pioli to be the coach is this: the probability of having a goal do player Belotti, player is equal to Belotti, coach is equal to Pioli. That for the conditional independence theorem, the theorem of the truncated factorization product, the one of the workhorse of our causal calculation, is given by the sum that you see on the last line. Probability of having goal if the player is Belotti and possess, because if you remember, the parents of goal, of outcome, the parents of outcome are the player and the possession and the situation. And at the same time, the probability of a given possession, a given situation, given that the player is Belotti and the coach is Pioli. Someone of you sees a problem in estimating these probabilities? I give you a hint. Andrea Belotti plays in Torino and Stefano Pioli coaches Milan. So where is the problem that we face? Leonardo, do you have any hint? Any possible explanation?
You will have no observations?
Absolutely. We have no observation. The probability of a given possession, if the player is Belotti and the coach is Pioli, is 0. We can't do the calculation. We have to force our mind and try to have another solution, because here we have no experimental data. Thanks. So what we do? We can insert a mediator. Remember that for practical reasons, an unobserved situation can be overcome by adding a mediator, by adding a variable by adding a variable to our graph. Generally speaking, there is a rule in causal inference, and we will see it written after. But the rule is, if my graph doesn't help me, if my graph and my data doesn't help me in assessing a causal relation, adding more arrows won't help. Adding more variables instead will. If I add more arrows, I mess up the situation and I won't help. I can add a variable instead and not a new arrow. So imagine what you do usually when you evaluate a person and you want to evaluate his possible performance in a new situation. What do you usually think about? You think about what he does better. You think about the actions that he performs or she performs. So in this case, how do you evaluate a football player? You often, when you look for a new football player for your team or for your Fantacalcio team, you evaluate it in terms of what he does. He's a left-wing player that runs from the defensive to the offensive stripe and crosses very well. If you have very good head strikers, very good head striker, tall players, good to strike, jumping and striking with head, then this would be a good player, a great player for your team. While instead, if you play in SSC Napoli, in which all the strikers minus Osimhen are all small and fast, probably someone crossing from the left or from the right is not a good option. So you try to evaluate the player in terms of the action that she or he performs. And of course, these actions usually can be systematized. You have a pass from a zone of the field to another zone of the field. You have a cross from a stripe to the center of the area. You have a free kick. You have a corner kick. You have a free throw-in that is something that has got a high probability of being performed and a low probability of being performed well. For some amusement about this, my advice is please go on the YouTube and look for an English player named Rory Delap. Rory Delap was is still alive, a football player for Stoke City that was a former javelin thrower. And he had this wonderful throw-in with the hands, arriving at about 40-50 meters. So from everywhere in the attacking zone, there was a throw-in for Stoke City. You would see all the strikers of Stoke City going inside the area because Rory Delap was preparing a sort of a missile arriving directly in the area. But usually this is an exception and would have an impact on a particular team. So you can, turning to our DAG, you can insert a mediator. You can insert a new variable that helps you in actually understanding what's going on. So what would be our new what-if algorithm? We have to calculate the probability of a given event in terms of its parents, in terms of the variables pointing into it. So now, what is now there is no more a parent player. There is no more a possession, a double arrow goal conditioned on player and coach. Now goal is conditioned on player and possession. On coach. There is possession. Possession. The probability of having a possession is given by role coach, not role player, not coach player. The role and the coach is something that we can calculate. Here by role I mean the action that the player performs. So the throw in, the pass, the headshot. Every player can be deconstructed into a matrix of behaviors, and we can express in these terms this matrix of behaviors. We can use this matrix of behaviors in order to express a single player. So in this way, we have shifted from a single player to a distribution, to a probability distribution. So we've got three terms that we have to calculate: the probability of having the goal given the player and the possession, his parents, that they are in the bottom part of the graph, if you remember, is the probability that the goal is scored if the player chosen is involved in a given possession. So the probability of having that possession if the player has a given role, so she does something, and the coach is the one training. To be complete, I would have to insert the current score, because depending on the current score, your player will behave differently. If you're leading 1-0 and you are towards the end of the match, you will never be forced to attack. You will try to preserve the ball and to do a little bit of melina, we say in Italian, to do a little bit of meaningless passes in order to make the time pass. And then the probability of role player, the probability of role conditioned on the player, the probability that that action is played by the player chosen. Of course, if the action is across from the left wing inside the area, if your player is Cristian Ansaldi playing in Torino, the probability will be very, very high. If your player is, let's say, Wojciech Szczesny, that is a goalkeeper, the probability will be very, very, very low. If your player is a center midfielder like Romelu Lukaku, then the probability again is very, very low. Lukaku likes to be in the center of the area or to receive the ball from the backwards and attack, not to cross from the left wing. It's not his work. So you have to deconstruct, and you can deconstruct the role of the player by the actions that he performs. So in this with this scheme, you can actually deconstruct. But in this, I give you a little room for subsequent intervention. And here I'm not speaking about something grounded. Here I'm speaking about active research that me, Luca Pappalardo, and Paolo Cintia are actually doing in the department. So if someone is interested in this kind of evaluation and would like or think that he could give his own contribution, and he's interested in this kind of calculation, please, we're here, and we would be happy to hear, to have possible help from you. Is a question and a matter of active research. Now, I will be a little bit nasty and go back to this situation. The situation in which you have no role. You have only a limited amount of data, and you can deconstruct your player into a matrix of behavior. You have just the situation. What I mean by situation? By situation, I mean the kind of possession that you perform. It could be a slow approaching with a fast acceleration at the end. It can be an action on the left wing. It can be an action, a possession on the right wing. It can be a sort of a tiki-taka advancement, or it can be a long possession in the center field with slow advancing, waiting for the right occasion, or it can be a shot from the distance, or it can be a free kick. You have got all these, but you haven't got the detail of the thing. And you want to evaluate the performance of a player that had never played with that coach. Could you imagine a way to do this? Is there a possible way to do this? Well, my answer is yes, but I would like before you to try to squeeze a little bit your head and try to understand if this is possible. I have my personal answer, and I would like to see if this is possible. Does anyone have a possible answer to this? The problem, I recall it, is that there is, the formula would be this, but I haven't got the way, and I can't directly estimate this probability. Is there a way? Can you imagine a way in which I can estimate this probability? Well, I'll give you my personal answer, and my personal answer is Bayes' theorem. We can't, of course, calculate the probability that I have the possession given that I have Belotti as a player and Pioli as a coach. But I can say always by Bayes' theorem that the probability of having Belotti as a player and Pioli as a coach conditioned on the possess, according to the condition on the possess, times the probability of possession divided by the probability of having Belotti as a player and Pioli as a coach. This is Bayes' theorem. I have not done nothing but applying Bayes' theorem. And you can say me, I didn't earn nothing, because still I have probabilities that I don't know. Because Belotti played never in a team coached by Pioli. And I can say you quite smiling, and this is where this is what can help you. Belotti never played in a team coached by Pioli. So what does it mean here? Someone of you has got a possible explanation? Well, Leonardo, you're my personal assistant. If you're still awake and not suffering from a probable yesterday drinks, can you like me, for example, can you bet about a probability, a possibility to calculate this?
I don't know. I was looking at the formula, and I think you have zeros, right? Because the probability of having player Belotti and coach Pioli would be 0, right?
Yeah.
You never observe it. And also the probability of having player Belotti and coach Pioli conditional on possess is still 0.
Yes.
So I'm not exactly sure on...
Okay. Now the trick is that if the probability of having them 0, what does it mean? That this probability are the probability of the player being Belotti and the coach being Pioli are independent.
Okay. Yeah,
so their joint probability probably could be estimated quite reasonably by the product of the marginal probabilities. Here I use reasonably because, of course, I have not experimental evidence. What I'm trying to do, I'm trying to build up a prior. I'm trying to build up my hypothesis. So thanks, Leonardo. So this is the trick that I will use. Due to independency, I can express reasonably the probability by the product. Why I did invoke the Bayes theorem? Because I can express the probability of something conditioned on something else by the product of the probabilities if I'm estimating that probability, not if I'm estimating the condition. So I couldn't separate this and make the product on this aspect when they were on the right side of the probability. Here, if you see. But I can do it. I'm perfectly allowed to do it here. So I can estimate this by products. And here I have the probability of having Belotti as a player if I am in that possess. And this I know because Belotti sometimes will participate in some possession. I have the probability in his own team that having the coach Pioli conditioned on possess. So I look for all the possession in the Serie A and condition on that possess. I look for the probability that Pioli is the coach leading them or ordering them, times the probability of the possess in all my championship, in all the Serie A, and then I divide it by the single probability of having Belotti on the field times the single probability of having Pioli on the bench leading. So this is a second way in which I can manage. Why all these stuff? And this is what we are going to look for in the second part of the lecture, in which we are going to recap all that we've done till now, and we're going to fix a little bit some ideas, because I want you to interiorize this concept that data are not enough in this kind of calculation. You have to put your own head, and your own head can be put in two different situations. The first one is drawing the graph. I draw the graph by my same knowledge of the word, of the rules of the word that I know, and I can test them by numerical means. But I have to draw them. I cannot rely on data and that's all, because I can do many things with data and only data, but not this kind of calculation. Causal calculation, I want to understand the cause given the effect, requires that you draw a graph, requires that you infer a model, a mechanism of how the world works. And as you remember, last time, me and Leonardo, probably if it was you, disagreed on a sign, on a direction in which the arrows were pointing. And this is perfectly fine, because we are two different persons and we are testing two different hypotheses. And we can test if our hypotheses are true when the data are sufficient. But there is a second way in which you can exploit your knowledge of the world, and this lack of data. And then you have to find a way to regroup the data in a smart way. And when you have to regroup the data in a smart way, so not adding variables like we did in the first part, but rather using less variables and try to estimate the probabilities, and try to build up matrix of probabilities and probability distributions, then my personal advice is always think about Bayes' theorem and independence condition, because if you've got a data, good. If you haven't got a data, try to reconstruct him by priors, by means of Bayes' theorem and independence rule, because this can help you at least in inferring a direction. Remember that we are estimating probabilities, that we are doing a causal inference, that we are trying to look at a direction, at an explanation, given data and given probabilities. We are not forecasts, we're not soothsayers, we're scientists. So we have hypotheses, conditions, and results that are due to our hypothesis and our condition. So we do not pretend to say this is the truth and the reality. We say, according to my hypothesis, condition, and calculations, this is the result. Hope that this can help. So I will stop here for the moment. We'll have a little break. I know that at 11 o'clock another interesting lecture starts. So we will take a 10 minutes break, and we will see here at around 10 and a quarter, and we will recap a little bit what we've done until now, and add one little piece of knowledge to our ability to deal with the graphs, and that is the ability to deal with time, with subsequent actions, and with subsequent possible evaluation in time. So thank you for your attention for the moment, and we will see you in 10 minutes. Thanks. Hello, so welcome to the second part, and here we will a little bit recap what we're doing, and try to remember the meaning of the operations that we do on graphs, and actually what we are trying to understand from our graphs and from our calculations here. I'm pretty sure that for what concerns the calculations, so the probability calculations and so on and so forth, you are perfectly able to do it by yourself, by just studying on the text that I've sent you. I've sent to the manager the text of the slides and the text of the several papers that will be helping you, and in the forthcoming I will give you many books that could be very useful to understand better, and as well as many software packages that can be used to understand better what's going on. But here we will try to take a little bit things from the beginning and trying to understand what we are actually doing with graphs, what the meaning of the graphs is, and what can be done with graphs, what cannot be done with graphs. So let's start. I would have prepared a sort of this kind of slide, but fortunately on the internet there is a very good lecture done by Felix Elwert at Harvard, and we will exploit this slide. Elwert did even published a very good recap on the meaning and on the utilization of causal diagrams, not complete but very well done, and I've provided it to the manager together with the slide of this lecture. So what we are remember, we assume that the DAGs, the directed acyclic graphs, are causal, and this is a very strong assumption, but it's necessary. Cause means, remember, one of the things that can help us in distinguishing cause from effect is that we have always to ask what comes first. One of the things that we cannot doubt in our real world is that the cause precedes the effect. The cause comes first. So this sometimes will give us, and we will see how, will give us problems when we face a cyclic cause and effect and cause and effect relationships. And we will see if that it is a problem if we want to know if it's the egg that causes the hen or it's the hen that causes the egg. But we will see. And I see that the administrator is making a wonderful joke about using the past and the future in the same sentence. You should have received an email tomorrow with the materials. Thanks you, Vittorio. That's exactly the kind of thing that I was going to say. So thanks for this wonderful joke. So as I was saying before, it can be shown that complicating a DAG by adding arrows to a given node set never helps non-parametric identification, but adding nodes, that is variables, like we did before, adding the role, the behavior of the behavior of people can actually help very much. So we will always try to remember this principle, adding arrows. Let's say in a George Orwell fashion, adding arrow bad, adding nodes good. Another very important thing to remember is that causal directed acyclic graphs encode the data generating model. Because in this model we encode the qualitative assumptions of the data generating model. Here we speak about quality. There can be a bunch of numerical models, that means a bunch of different equations that represent these arrows. This model only means that in the formula that I use to calculate C, only the variable t and x do enter. These mean the arrow, but there can be many equations that can represent these arrows. And if there are not equations, remember, as we are doing in this lecture and in my approach, we use probabilities. We are, of course, data scientists and we love using probabilities, but these arrows can be equations, and a lot of equations. What the model does say is only, oh, you want to calculate y, then you have to know x because of this arrow, c because of this arrow, and u1 and u2 because of these arrows. And this is another very important aspect. Of course, when building a model, you must consider all factors that play a role in data generation, regardless of whether they are observed or unobserved. Because what can happen that if you draw a graph, a partial graph, and you do not put the unobserved variables, and then you go to test for conditional independence, you find that the variables are not conditional independent. So you are missing something, you are missing some relations. And this means that even arrows are missing, or even unobserved variables are missing. But if you know that there are unobserved variables, and you don't put them into play, then you can't complain for the fact that your graph do not respect independence with the graph, do not respect conditional independence, because in fact the graph that you draw is wrong by your own assumptions, according to your own assumptions. So you have to do something different. So please follow the advice of Elwert, which is a very good advice. Do not reason backward from the variables to what that can justify them, but consider your inner model of the world. Your inner model of the world is the one that you want to test. Remember to test if it helps with prediction, if it helps with understanding. Of course, like we were saying before, assumptions are unavoidable. And where assumption is, if you're not willing to make assumptions, we cannot identify causal effect, because assumption-free causal inference is impossible. But where are assumptions? Where assumptions are, assumptions are in deleting arrows. Here you see, you can always do a complete DAG. A DAG in which every variable is connected to other variables in a time-consistent fashion. But this kind of graph could not help us. If I connect with bidirected edges, all the variables, I go nowhere. If I connect all the graphs, in a time-consistent fashion from the parent to the child, so I suppose U1 and U2 are the first in time, then comes X, then comes T, then comes C, then came Y. Well, this may work if we've got sufficient data. But if we haven't got sufficient data, this can result in a mess. So please, assumptions. Try to model your world as simple as it can be to explain the things, but not simpler. Do assumption, be a gardener, cut all the arrows that may be insignificant or that are, in your opinion, not important. This is very important. Another thing that we do, and this is very important to remember, is that we are suppressing independent errors. We usually omit the set of the error term that is usually independent on each variable, because of course they don't help with the non-parametric identification. But if these independent error terms are there, they can mess up things on a numerical fashion. And so it can be shown that sometimes we should see a particular causal effect and we do not see it just because of independent errors. So here, from the reasoning that we have, in the reasoning that we have done, so on and so forth, numerical error has never been cited. Remember that when dealing with the real world, you would have to do this, and you would have to state what would happen if a completely random relation would apply. So my personal advice, like we were saying in one of the first lecture, we were speaking about mutual information, is ever compare your results with the completely independent situation where everything does depend on nothing, with the complete messed up situation, because numbers we know are important and errors can be everywhere. So this is a different point of view of directed acyclic graph. We can interpret these graphs as a visual representation of non-parametric structural equation models. So each variable, as we were saying, is generated by a structural equation model that relates the variable to its parents, like we were saying, and to an error. So the value of the variable v is related by a function to the values of the parents, of her parents, and to an error. And if the error is stochastic, then you have a set of stochastic equation. If you have an error term, if you give an error term, then you have a deterministic situation. But you can think, if some of you is more prone to think in terms of equations than in terms of graphs, please remember that this is an alternative situation of seeing it. You see the variable as a function of the parent variables plus an error. So in this case, how can you represent this graph? U1, of course, is just a function of its error, and so U2, because they are unobserved. So only error term here. X is a function of U1 and U2, the unobserved variables. Unfortunately, we will have to deal with them further, and of the error and the measure of X. T, this is a lucky situation, is a function only of X and on the error, the independent error that insists on the measurement of T. C is dependent on T, and here I disagree with Elwert that puts even X in the evaluation of C. Oh no, sorry, there is an arrow that points from X to C. I'm sorry, but my blindness was not allowing to see this. So there are two arrows, and both T and X that are parents of C do entering, and then Epsilon has got three parents. There are four parents that are C by this arrow, that is X by this arrow, this time I saw it, and then U1 and U2. So this is another alternative way to look for directed acyclic graphs. And of course, as we were saying, a qualitative directed acyclic graph is consistent with multiple quantitative models. The same set of arrows can be cast into a bunch of multiple equations. So if you see here, relating C with T and X can be done with this simple formula, of course, But even with this rather absurd formula with a factorial x and the root of t, of course, and this is perfectly fine. This, we are not doing any error here. This qualitative functional mechanism, functional connections, is consistent with many functional mechanisms. When we deal with probabilities, we do not care about these equations because we have probabilities. So we have that. Remember, marginal probabilities give the distribution of the variables, and conditional probabilities give the mechanism, give the arrows. So this was for what a general scroll with some recalling of the properties of the directed acyclic graph, and on some point of view, and recalling some point of view about what is a directed acyclic graph and how we can connect it to the mathematics that we know for structural equations, or without parameters, so only functions, or with probabilities. We're going to go a little bit faster, and of course, this lecture, this presentation is very well done, so quite better than my poor presentation were. So I sent this to the manager, and you can access it. But we will look specifically to one criterion, and we will see what it means in practice. The adjustment criterion is a complete criterion that says that, okay, we want to understand and we want to know, first of all, if given my graph, I can identify the causal effect of x, here he says on t, on epsilon. I want to understand the total causal effect of a variable on another variable. And the first thing that I have to ask me, if I'm convinced that my graph is correct, is it is possible? And formally, their answer is that it's possible. The total causal effect of t on epsilon is identifiable if one can condition or adjust for a set of variables z that blocks all non-causal paths between t and epsilon without blocking any causal path between t and epsilon. And this is the formal answer. This set of variables we saw last time, and that may be empty, remember all this. If there is no need to condition, do not condition, fulfills this adjustment criterion relative to the total causal effect if Z blocks all non-causal paths and no elements of Z is on a causal path from T to epsilon, or descends from a variable on a causal path from T to epsilon. So, of course, we can test ourselves, and I invite you to try to test yourself, trying to understand when these actions, the action of x on epsilon, can be identified. Does some of you can or want to infer or want to try to answer to these questions about these four graphs? Can you infer if there is here a graph in which the effect of x on epsilon can be unidentifiable, that is, there is a situation in which, oh, no, I can't do nothing. Do you see any of these graphs in which the situation does not allow you for any hope? Is there any volunteer that wants to reason with me about this kind of okay, I will give you a hint. The graph in which I cannot, for sure, infer a causal effect of X on Y is the fourth graph, the graph on the bottom. Okay, Leonardo, tell me please why. Oh, sorry, yes. Okay, now you can speak, please.
Okay, I'm the usual suspect.
Yes.
Yeah. At the beginning, I thought the first one, well, many of them would be unidentifiable. Then I realized just that they have no effect, right? Because the arrows, there is no path, in a sense, directed path
Exactly.
from X to Y, but it's still identifiable, right?
Exactly.
And in the last one, I think the problem is that we have an unobserved effect. Well, we have an observed U1 that has no mediation with Z1. So we cannot distinguish, in a sense, the effect on Z1, I guess. Or is that not the right answer?
This is the right answer, exactly. Because we have an unobserved effect between X and at least one of his direct child. And this is the first thing that you should watch, that you should spot when you look on a causal graph. Thanks, Leonardo. We are going to watch now what is the main line of reasoning. So, when can I identify whether X causes Y? In all the graph that you see here, the effect of X on Y is identifiable because you see that the child of X, the direct child of X, are not reachable by a pathway that involves only bidirected arcs. A bidirected arc, remember, you can always watch it as an arc with an unobserved variable in the middle. Okay, when I see a bidirected arc, it means that I have an unobserved variable here that I cannot measure, and that makes fabricates this spurious correlation between X and Y or X and Z. So in this situation, typical models in which the effect of X on Y is identifiable, in all this situation, the causal model is identifiable, and the good novel is that it can be done algorithmically. So what we've done in this lecture was an introduction to learn to reason about how we can cut some arrows and add some variables. But if you have a graph, remember, if you have a graph and it can be algorithmically decided if it is possible to get a causal effect of X on Y or not. And in this case, the effect of X on Y is identifiable because there is not the bidirected path between X and at least one of its children. While here you see that in these graphs, the effect is not identifiable. For example, take graph A is trivial, okay? But take graph C. The effect, there is a bidirected path from X to Z. So Z is one of the child of X, at least one of the child of X is connected by a bidirected path, not identifiable. Look at G or at Y, or look at G or at F. Here, X is connected to Z1 by a directed edge, but it is possible to jump from X to Z2 and to Z2 to Z from Z2 to Z1 only by following by bidirected paths. So, no, I can reach a child of X, because you see that Z1 is a child of X, only walking on bidirected paths. So this graph is not identifiable. So this is the first thing that you should look for. And if you are in the situation like this, and you say, okay, the only child of Z1 is not reachable by walking only on bidirected path, but it's a mess. Remember that there's an algorithm, and this algorithm is discussed in a very good paper that I sent to the manager, and that you can watch and study, and that there is programmed in I think for sure in R is programmed, and I would like to program it in Python in the next future. So you may ask, why don't you illustrate us this algorithm? And the answer is, it would require me about 7 or 8 hours. So having 12 hours of lectures, I can show you, if you want, in the next future, the general principle of the algorithm, but it would be really a pain on an online lesson to explain this algorithm. We can, of course, discuss it, and I can help you in digging into, but it would be probably not an intelligent move from me to try to explain and demonstrate this algorithm on a lecture online of 7 hours. So I think you can forgive me, but we can discuss it. And before going to the last argument, I would like to remember you that you can always, you have my mail, Vittorio can send you my mail, and you can contact me for clarification or for questions or for answer of books or papers. And because these disciplines, these methods of causality, are still in their infancy, they will be used maybe in infantry, but they're in their infancy. And it's sometimes difficult to try to orientate and find your own way in how to use them. Sometimes you have the sensation or the grasp that, yes, they can be used for your problem, but you don't know exactly why, or you have some technical doubts. And if I can, I'm here to help. And it would be, of course, if you require to, if you understand all by yourself and you want to go by yourself, this is the best result that a lecturer can obtain. So I would be quite happy for. But I don't know if this if you saw the slides that I was showing you, because I see that the condivision has been suspended. I hope that you were able to see what I was showing you. Okay, thanks. Okay, So we go to the next and very last argument, and this is an argument that I will touch slightly, but that can be interesting, and is whether or not an effect on can be identified in different times. Here I'm sorry that 2 arrows are missing, but I will fix it. So suppose that I have some health problem, for sure. Usually, you know, in causality, and sometimes we speak about football, but sometimes we have to speak about diseases. So suppose that we've got this situation. You have a disease, and you are given some treatment. So imagine that a simplification is you have an illness, and X1 and X2 are the treatment. You are given a given treatment, a given drug, a given medicine. Oh no, this is not correct. Sorry. Thanks. Okay. Sorry all. This is the correct slide. I hope that now you can see it all. Thanks, Leonardo. Suppose that you've got this graph. X1 and X2 are the treatment that are given you in subsequent times. So first you get X1, then you are evaluated, then you get X2. You are evaluated thanks to Z, if you show or if you show not some symptoms. For example, the symptom could be fever. Suppose that you have an infection, you are treated with an antibiotics or paracetamol. Suppose the first treatment is paracetamol, and then you look for Z in order to see if you have fever. Z is the fever, is the symptom. Of course, there are hidden variables. U1 represent your history as a patient, so the disease that you have, and U2 represent your condition after the treatment and the disposition to recover. So suppose, for example, for a simple story, that you have an infection. You're given paracetamol as a first pre-treatment, as a first treatment, and the physician look if you still have fever after 2 days, and the answer is yes, the patient has still fever. So the physician decides you to administer antibiotics, and then you recover, because at the first time you were given a treatment that is only symptomatic in order to see if things were going on the right side, and then after the fact that you still show the symptoms, you are given a different medicine. It is often the case in medical treatment or in dynamic control treatment that you give a first treatment. You give a first treatment, X1, you want to evaluate the evolution of the situation before doing some other treatment. And this other treatment or another dose of the same treatment depends, of course, on the first treatment. Which was the first treatment? If I gave the first treatment was water with sugar, the second treatment could be paracetamol. But if the first treatment was paracetamol, probably it's useless to give another or the same dose of paracetamol. And this is conditioned on Z, on the symptoms that you show that are, of course, dictated not only by the treatment that you are given, but even by your patient history, so the disease that you have and your general health condition before U1 and after U2, the first treatment, because you see that your condition are point toward X1, the first treatment, but are conditioned in a way that you don't know by U2. For example, if you give paracetamol to a patient that has got some liver disease, you could not have done the best thing in the world. Because paracetamol can be really harmful in high doses to the liver of the patient. So you want to understand if there is a way to estimate the causal effect of this, and the answer is fortunately yes. Here I'm citing the Elwert article that is very clear, but just to give you the feeling that this can be done. This is the sequential backdoor criterion. So we can apply the backdoor criterion sequentially in time. You begin considering the first unit treatment, and then you redraw the graph, deleting from the original DAG all arrows into future unit treatments, 81, 82, and you check if the total causal effect of 80, the first treatment, on epsilon in the redrawn DAG, in the DAG that you draw with deletion of arrows, can be identified by the backdoor criterion. And if this succeeds, and then you go subsequently. So, for example, if you want to understand here, what you do, you look at the possibility of applying, the backdoor criterion by just deleting two arrows and by just deleting this arrow and this arrow, the arrows that are pointing towards X2, and you look if the backdoor criterion can be applied. Then you go further, and of course here we have got only X1 and X2, but if we have multiple intervention in times, we do the following things for all the intervention in time, and then you just look for you just apply the backdoor criterion sequentially in time. Is like saying that you are looking at the same intervention with the backdoor criterion given the treatment 1 and only that, and then treatment 1 and treatment 2 and only that, and so on and so forth. And you multiply the effect of the overall treatment by all his history, by all the history of the preceding treatment. So this is the meaning of the sequential backdoor treatment that is explained very well in the article of Elwert that I shared with you, and I invite you to look at this. And this is because even if you don't properly understood with this fast and furious explanation, the fact is that you can, with the causal diagrams, you can deal with dynamic control situation in which you do X at time 1, X at time 2, X at time 3, and so on and so forth, and you try to evaluate in the run of time if what you're doing is worsening or is raising your the effect of what you're doing, if you're doing best or you're doing worse. So we are at the end of our lecture. So in the next two lectures, we will see some different way of deal with causality with time series, and we will do some experiment. We will show some examples in order for you to take to get a grasp of what we're doing. If there are questions, if there are arguments that you would like me to go back, or if you saw any kind of mistake or misinterpretation in what I've done, please write me. Vittorio will give you the address, and we can fix for it. We can try to see if there is way for intervention, and we'll try to understand if we can all together understand it better. I thank you all for your attention, and we will see next Tuesday on 9:15 to complete our lectures. Thank you all.